In this video, we will discuss the calculations for the heats of neutralization experiment. There are three parts of this experiment, and we will work through the calculations for all three of these. The first calculations are for part A, where we determine the heat capacity of the calorimeter. We require this value in order to perform the remaining calculations. The heat capacity of the calorimeter is found as the heat absorbed by the calorimeter divided by the temperature change of the calorimeter, or Ccal is equal to Qcal divided by delta T. Recall that we used two different temperatures of water for this part. The heat absorbed by the calorimeter is the difference between the heat lost by the hot water and the heat gained by the cold water, or Qcal is equal to Q hot minus Q cold. We can calculate the heat changes in the water samples by using the equation Q is equal to C times M times delta T. Here, M is the mass of each water sample, which was 50 grams, since we had 50 milliliters of water each with a density of 1 gram per milliliter. Capital C is the specific heat of water, which has a value of 4.184 joules per mole per degree Celsius. Our data from part A from the previous video are shown in the table. The temperature of the cold water initially was 23.2 degrees Celsius. The temperature of the hot water initially was 39.8 degrees Celsius, and the final temperature of the mixed waters was 31.3 degrees Celsius. So let's begin with the hot water. First, we need to calculate delta T for the hot water. This is just the temperature of the hot water minus the final temperature of the mixed water. These values are 39.8 degrees Celsius minus 31.3 degrees Celsius, for an overall delta T of 8.5 degrees Celsius. At this point, we can calculate the heat lost by the hot water. Q hot is equal to C times M times delta T hot, or 4.184 joules per gram per Celsius times 50 grams times 8.5 degrees Celsius. The final value of Q hot is found to be 1.78 times 10 to the 3 joules. We can now repeat the same calculations, but for the cold water. Delta T cold is equal now to the final temperature minus the initial temperature of the cold water, or 31.3 degrees Celsius minus 23.2 degrees Celsius. The overall value of delta T cold is found to be 8.1 degrees Celsius. The heat gained by the cold water is Q cold equal to C times M times delta T cold, or 4.184 joules per gram per degree Celsius times 50 grams times 8.1 degrees Celsius, or 1.69 times 10 to the 3 joules. The amount of heat gained by the calorimeter is just the difference in these two values, or Qcal is equal to Q hot minus Q cold. We can substitute the values in 1.78 times 10 to the third joules minus 1.69 times 10 to the third joules, giving us a final value of 9.0 times 10 to the 1 joule. The last step in part A is to calculate the heat capacity of the calorimeter. We do this by dividing the heat gained by the calorimeter by the change in temperature of the calorimeter. Since the calorimeter started at the same temperature as the cold water and ended up at the same temperature as the combined water, the temperature change for the calorimeter is exactly the same as delta T cold. Thus we have Ccal is equal to Qcal divided by delta T cold, or 9.10 times 10 to the 1 joules divided by 8.1 degrees Celsius, which gives a value for the heat capacity of 11.1 joules per degree Celsius. We can now look at the neutralization of hydrochloric acid with sodium hydroxide. The enthalpy of neutralization for this reaction is calculated as delta H of neutralization is equal to Q for neutralization divided by N of HCl, where Q neutralization is the heat generated during the neutralization reaction, and N sub HCl are the number of moles of HCl neutralized. Recall from the previous lecture that during the neutralization reaction, the heat generated is transferred to two different parts. One is the solution itself, and the other is the calorimeter. As a consequence, we have two terms in our expression for Q neutralization. The first term, C times M times delta T, is just the heat gained by the solution. The second term, C cal times delta T, is the heat gained by the calorimeter. From the previous video, we know that the data for part B are: the temperature of the NaOH initially was 23.2 degrees Celsius. The temperature of the hydrochloric acid initially was 23.5 degrees Celsius. And the final temperature after neutralization was 29.8 degrees Celsius. The first step is to calculate the temperature change during the neutralization reaction. Since the acid and the base were at slightly different temperatures, we have to first calculate the average temperature and use this in our delta T calculation. We find the simple average of the two temperatures as 1/2 times the temperature of the sodium hydroxide plus the temperature of the hydrochloric acid, or 1/2 times the sum of 23.5 degrees Celsius plus 23.2 degrees Celsius. The average value is found to be 23.4 degrees Celsius. The change in temperature is the difference between this value and the final temperature, or delta T is equal to T final minus T average. When substituting our values, we find we get 29.8 degrees Celsius minus 23.4 degrees Celsius, or an overall delta T of 6.4 degrees Celsius. The next step is to calculate the total heat generated by the reaction. Q neutralization is equal to the specific heat of the solution times the mass of the solution times delta T, plus the heat capacity of the calorimeter times delta T. Both the acid and the base are in aqueous solution, and so we can make the assumption that the solution has the same specific heat as water, or 4.184 joules per gram per degree Celsius. We have 50 milliliters of both the acid and the base, which gives a total volume of 100 milliliters. Assuming the density of water is 1 gram per milliliter, this means the mass of the solution is 100 grams. We're now able to solve. Q neutralization is equal to 4.184 joules per gram per degree Celsius times 100 grams times 6.4 degrees Celsius for the solution, plus 11.1 joules per degree Celsius times 6.4 degrees Celsius for the heat capacity of the calorimeter. This gives 2.68 times 10 to the third joules plus 71.0 joules, or an overall Q neutralization of 2.75 times 10 to the third joules. Before we can solve for the enthalpy of neutralization, we need to find the number of moles of hydrochloric acid that were neutralized. To do this, we need the concentration of the hydrochloric acid, which was 1 molar, and the total volume of acid used, which was 50 milliliters. The number of moles of hydrochloric acid is just equal to the product of the concentration times the volume, or 1.0 molar times 0.0500 liters, which gives 0.0500 moles. Finally, we can solve for the enthalpy of neutralization. Delta H of neutralization is equal to Q of neutralization, found on the previous slide, divided by the number of moles of HCl. This becomes 2.75 times 10 to the third joules divided by 0.0500 moles, or 55.0 times 10 to the third joules per mole, which is equivalent to 55.0 kilojoules per mole. We can now complete part C, the neutralization of acetic acid with sodium hydroxide. As before, the enthalpy of neutralization for this reaction is found to be delta H of neutralization is equal to Q for neutralization divided by the number of moles of acetic acid that were neutralized. As in the previous part, the heat generated during the neutralization reaction is transferred to two different parts, the solution and the calorimeter. So our overall expression for Q neutralization is exactly the same. C times M times delta T for the solution, plus C cal times delta T for the calorimeter. Again, our data from the previous video are shown in the table below. The temperature of the sodium hydroxide was initially 23.5 degrees Celsius. The temperature of the acetic acid initially was 23.7 degrees Celsius, and the final temperature was 29.8 degrees Celsius. As before, we must first calculate the average temperature of the two solutions in order to use this to calculate delta T for the neutralization. The average is just 1/2 times the sum of T for sodium hydroxide and T for acetic acid, or 1/2 times 23.5 degrees Celsius plus 23.7 degrees Celsius, or an average temperature of 23.6 degrees Celsius. The change in temperature is the difference between T final and T average, or 29.8 degrees Celsius minus 23.6 degrees Celsius, which gives an overall delta T of 6.2 degrees Celsius. We can now calculate the total heat generated by the reaction using the same formula for Q neutralization. Once again, we make the assumption that the specific heat of the reaction mixture is just equal to the specific heat of water, and that we have a total mass of 100 grams of solution. Substituting these in, we find that Q neutralization is equal to 4.184 joules per gram per degree Celsius times 100 grams times 6.2 degrees Celsius for our solution, plus 11.1 joules per degree Celsius times 6.2 degrees Celsius for the calorimeter. This gives 2.59 times 10 to the third joules plus 68.8 joules, for a total Q neutralization of 2.66 times 10 to the third joule. The number of moles of acetic acid that were neutralized are found in the same way as in Part B. We need the concentration of acetic acid and the total volume of acetic acid that was used. The number of moles neutralized is equal to the product of the concentration times the volume, or 1.0 molar times 0.0500 liters. This gives a value of 0.0500 moles neutralized. And lastly, we can solve for delta H of neutralization as Q for neutralization divided by the total number of moles of acetic acid neutralized. When we substitute in our values, we get 2.66 times 10 to the third joules divided by 0.0500 moles, which gives a value of 53.2 times 10 to the third joules per mole, or 53.2 kilojoules per mole. This concludes the calculations for the heats of neutralization experiment. You will be provided with report guidelines and a data sheet in the coming days on Canvas. The report guidelines will walk you through the exact same calculations we just performed, and will also indicate that you need to calculate the percent error for your calculated value and the actual heat of neutralization for each acid. These values will be provided for you.